Good morning, welcome to a new lecture. Today I will solve several problems. Assume we have one object which is hanging from ceiling. That object it is one triangle plate, and we attach to the ceiling using 3 rods. This object is assumed it is one triangle plate and it is rigid. We apply external load. External load, it is known. We show the magnitude with P, and dimension here it is L and L. It means the P we apply exactly in the center. Dimension here, assume this is L, this is 2L. So this rod in the middle, the length is 2L, two others, the length is 3L. Young modulus for this one it is E, cross-sectional area it is 2A. For this one it is E, cross-sectional area is A. For this one again it is E, cross-sectional area it is 2A. It means the material is the same. For example, all of them from still the same still. So the Young modulus it is the same. Cross-sectional area for these two corner one it is 2 times of the middle one. So these are 2A, this is A. Let's put name for each rod. This is rod 1, this is rod 2, this is rod 3. What will happen if I apply P here? If I pull this system, what will happen? This rigid plate will move down and it will not rotate. Why? Because it is symmetrical system. You see, material is the same, cross-sectional area 2A, 2A, it is A, load exactly in the middle, so there is no reason to rotation. They will deform all together, and the amount of deformation in rod 1 will be equal to rod 2, will be equal to rod 3, and this rigid plate only will move downward. So in that case, if I want to find internal forces in each rod, I want to find F1, F2, F3. In terms of P external load it is known value, but F1, F2, F3 they are internal forces, they are unknown. How I can find it? Because it is in plane structure, I can write summation of forces in the vertical direction. If I write this, I will end up with F1 plus F2 plus F3 is equal to P. That is one equation, equation 1. Another equation, I can write summation of moment respect to one point. For example, here point A is equal to 0. In that case, I will have F2 times L plus F3 times 2L, 2L minus P times L, or I can take to other side, is equal to PL. This is second equilibrium equation. Here we have 3 unknowns, F1, F2, F3, F2, F3, but we have 2 equations. 3 unknowns, 2 equations. The number of unknowns more than the number of equations, so we cannot find F1, F2, F3. We need extra equation. This kind of system, the number of unknowns is greater than the number of known. We will call it indeterminate structure. So if the number of unknown is equal to number of equation, in that case we can find those unknowns. Those structure we call it determinate. If the number of unknowns are greater than the number of knowns, in that case we cannot find unknowns only using equilibrium equation. Those kind of structure we call it indeterminate. Indeterminate structure. So in indeterminate structure we will need additional equation. Those equations we will call it compatibility equations. So these are equilibrium equations. We will need compatibility equations. Compatibility equations comes from deformation of structure. We should understand how structure will deform. Here, this will move down. So this point will come here, this point will come here, this point will come here, and we will have delta 1 here, we will have delta 2 here, and delta 3 here. And in this structure, delta 1 is equal to delta 2 is equal to delta 3. What is delta 1? Force in this member times length divided by EA. So it will be F1 times 3L divided by 2EA should be equal to F2 times length 2L divided by EA. That should be equal to F3 times 3L divided by, again, 2EA. Now we have three equations. We have three unknowns. We can find F1, F2, F3. This way I can solve the problem, but I will end up with solving three equations, three unknowns, and you see the procedure will take long time. Here in this problem, this way, to solve this problem, we will call it force method. We are finding the force. But I can solve this problem very fast using stiffness method. How? Let's I will solve using the stiffness method. Using the stiffness method, I will look at the axial stiffness of each member. Axial stiffness formula is Young modulus times length divided by length. For member number 1, Young modulus times 2A divided by 3L. So K1 will be 2EA divided by 3L. K2 stiffness, axial stiffness for member 2 will be EA over 2L. Axial stiffness for member 3 will be again 2EA over 2L. 3L, sorry, the length. 2EA over 3L. So if I assume EA over L is equal to the K, this will be 2 over 3K. This will be K over 2. This will be again 2 over 3K. So now look at the problem. If I assume each of these one is spring, how is deformation? Deformation in spring 1 is equal to deformation in spring 2, that is equal to the deformation in spring 3. So we have 3 springs, they deform together. The amount of deformation in each spring is equal. So this is the concept of the combination of spring as a parallel. So we attach these 3 springs, these 3 springs, they are parallel. We attach like parallel spring. If we attach like parallel spring, so now we know what is the total deformation. Total deformation will be total force divided by total stiffness or effective stiffness. Total force here, external force is P. Total stiffness is K effective is equal to K1 plus K2 plus K3. If I add these together, I will have 2 over 3K plus K over 2 plus 2 over 3K. So from here, deformation will be equal to P divided by, this will be 6, yes, that will be 4K plus K plus 4K. So from here, delta will be equal to 6P divided by 9K. 4K, 4K, it will be 8K plus. I made one mistake here, sorry. This will be 6 divided by 3, 2, 4K. 6, this will be 3K. 3K. So this will be 4K, 4K. It will be 8K plus 3, it will be 11. So 11K. Everything is right, I hope so. And you can double check now. Total deformation will be 6P divided by total stiffness, because they are parallel. We add stiffness together. If we add stiffness together, we will end up with total or effective stiffness. Total force divided by total stiffness will give us deformation. Now we have deformation. So what is the force in spring 1, or what is F1? F1 is equal to stiffness of that spring times deformation. So will be 2 over 3K times this delta, which is 6P over 11K. K and K, they will cancel each other. 3, this will be 2, it will be 4P over 11. What will be F2? K2 times delta. So that will be K over 2 times delta 6P over 11K, and so on. You see, immediately we can find internal forces in each member. This way I solve it, we will call it stiffness method. Let's look at another problem. Another problem, we have one rigid beam. This rigid beam has 2 spring support here and here. Stiffness is K, K, and this K is given, it is equal to E A over 4L. We have another bar, inclined one. The young muscles for each rod, it is E. Cross-sectional area is A and A. The length is L and L. This angle is 60 degree. This angle again, it is 60 degree. This system is subjected to external load P at mid-span. In the following structure, determine the internal force in the spring. We want to find internal force in this spring. You see, this is again symmetrical system. this rigid beam only will move down, and the formation in all of these members will be equal. So after we apply this load, the beam will move here. This deformation will be delta. Again, this deformation will be delta. Both, they will deform same value, equal value, and that is delta. Again, we will have elongation in this bar and in this bar. And the elongation magnitude in the vertical direction will be equal to the delta and delta in the vertical direction, not in the rod direction. So, this is the meaning of, we attach these as parallel spring. Combination, it is in parallel. So, if it is combination in the parallel, the effective stiffness is summation of stiffness of these members. So, the summation of stiffness, we will have two springs, so 2 times this value. Each one it is EA over 4L. This will be stiffness of these two springs. We add together because each one it is EA over 4L. I will multiply by 2. For each inclined bar, if you remember, I proved that inclined bar stiffness, it is EA over L cosine square alpha in direction of load. So, if this is inclined bar, this is our LEA, and this is load direction. This angle we call it alpha. So here alpha is this angle, which is 30 degree. So stiffness of each one will be EA divided by L length times cosine squared. Alpha here is 30 degree, and how many of these we have? 2 of them. Multiply by 2. This will be our total stiffness. Now, deformation delta will be total load, external load, which is P, divided by effective stiffness. That will be P divided by 2EA 4L plus 2EA over L cosine square 30. Now, if we want to find force here in this spring, and I call force in this spring, for example, F1. F1 will be equal to stiffness of that spring which is K times deformation delta. I have K, I have delta, I can find F1. This is again stiffness method. You see, using stiffness method, I can solve this problem very fast. Let's look at another problem. I have one rigid beam . We support this rigid beam using one hinge support here and 2 parallel bar . these are parallel, assume this is 30 degree, this is 30 degree, and this is rigid beam, is subjected to external load here, P, from here to here, here, and here each one is lowercase a. Lowercase a, this distance is known, P is known value, the angle is 30. This is member 2, this is member 1. Internal force here I will show with F2. In this I will show with F1. Point A, point B, point C. The Young modulus for each one it is E and E. Cross-sectional area it is A and A. Problem statement asks, determine the ratio of F1, internal force in member 1, over F2. This is unknown. How we will find this? In order to find that, first we should look at today the formation of this structure. This structure, this member, will rotate respect to C, and it will deform like this. So point B will come to the point B prime, point A will come to the point A prime. This will be the formation for point A, I show with delta A. This will be the formation for point B, I show with delta B. From geometry, I know in these two triangles, one this triangle, another the bigger one, I can write delta B over delta A is equal to 2A over 3A. Delta B divided by delta A is equal to 2A divided by 3A. I know I can write that. Another things I know, from here to here it is 2A, but I don't know the length of this member. That member length, if it is L2, L2 cosine 30 should be equal to the 2A. So L2 will be equal to 2A divided by cosine 30. From point C to A, it is 3A, but I don't know this length, but I can find it. If that length it is L1, L1 cosine 30 should be equal to 3A. From here, I can write L1 is equal to 3A over cosine 30. So I know L1 in terms of A. A is unknown, everything is, A is known, everything is known, so L1 is known. Here again, A is known, everything is known, L2 is known. So L1 and L2 I found in terms of A, lowercase a, which is known. So now L1 and L2, both they are known value. Let's look at here. From geometry, we figure out deformation at point B over deformation at point A is equal to 2A over 3A. A and A, they will cancel. So it is equal to 2 over 3. What is deformation at point B? Deformation at point B, this deformation will be equal to what? Will be equal to component of this, not even I can find that. Let's, deformation of delta B, this deformation will be equal to force here we apply at point B divided by stiffness of this member in vertical direction. How much force, if we apply P here, external force here, because of this force, how much force we have here and how much force we have here. Can we find that or not? If I apply force P here, okay, the external force because of this P here at point B, if I call it, for example, FB, is known value or not? It will be, FB will be equal to vertical component of F2. It will be F2 sine 30. How about force here at point A? FA will be F1 sine 30. So, if I apply external force P here, external force here P, I'm pulling down, that external load will apply load at point B and point A. And because of that load, we will have deformation at point B and we will have deformation at point A, and this rigid beam will rotate respect to point C. That external load here at point B will be F2 sine 30 if I assume internal force here is F2. I assume internal force here is F1. So here the force will be F1 cosine 30 will be load here at point A. So I can write delta B is equal to force at that point FB divided by stiffness of this member in the vertical direction. Stiffness of that member in the vertical direction will be EA divided by L2 times cosine square of this angle. This, if this is 30, this will be 60. So cosine square of 60. In similar way, I can write delta A is equal to FA divided by EA over L1 cosine square of again 60, because this angle will be 60. Now instead of FB you can plug F2 sine 30. Instead of FA you can plug F1 sine 30. So you have FA, you have FB, you have L2, you have L1, you can plug here, and a lot of terms they will cancel each other, and finally you can find ratio F1 over F2. Let's rewrite everything here. If I plug here, delta B over delta A is equal to over 3. From here I can write F2 sine 30 EA divided by 2A divided by cosine 30 times cosine square 60 divided by F1 sine 30 EA over L1. L1 will be 3A cosine 30 times cosine square 60, that is equal to 2 over 3. You see the terms, they will cancel each other. Sine 30, they will cancel each other. Cosine square 60, cosine square 60, they will cancel each other. This cosine 30, this cosine 30, they will cancel each other. A and A, they will cancel each other, and you can simplify, and you can finally find F1 over F2 ratio. Okay. These, they were sample problem I solved using stiffness method. I will solve more problems next session. So see you next session. And thank you so much for watching this video. Bye bye.